Right, this is example 7 on page 109 in your textbook. If you want to get the full wording, then look it up in there. But we have a sphere A of mass 2 kilograms moving with speed 6 meters per second collides obliquely with a sphere B of mass 4 kilograms. Just before the impact, B is stationary. So what that means is that after impact, the sphere B will move along the line of centres. So it's just worth bearing that in mind, because the impulse is acting in that direction. So we'll move along line of centres after impact. A makes an angle of 60 degrees with the line of centres of the two spheres. So to draw that, you really need to pop in your line of centres coming through, and that's important to all of these questions, and then angle 60 degrees. And the speed is 6. Like so. And then the way to split these is to think about what's happening perpendicular to the line of centre and parallel to the line of centres. So the perpendicular doesn't change. E is a quarter, and we want to find the velocity of A and B immediately after the impact. So you know that vertically A is going to be moving in this direction. Well, it won't be moving in this direction, but the component in this direction will be 6 sine 60, because that remains unchanged. We need to find the component in this direction, which I'm going to call V, and we also need to find out what's happening to B. So again, we've got this line of centres that's running through here. So we're looking at just before, just after impact, but I would draw them as being separated out, I think. It seems to come out better that way. So call things what you want, but I think we've pretty much been using V and W, haven't we, for these? And we also need to think about having a positive, negative direction. So most of the motion's this way. So we take that as being a positive direction. You don't necessarily know that it's going to be moving this way, but just as long as you're consistent, it will all come out in the wash. And if A actually bounced off B and went off that way, your V is going to come out negative. So that should all be okay. So parallel to the line of centres is where we're looking. So we're basically working with momentum and restitution. That's what we've got to work with. So momentum. So momentum before equals momentum afterwards. So 2 times 6 cos 60 is going to equal 2v plus 4w. So mass times velocity. That gives you 3 equals v plus 2w. When you simplify that down. And that's our first equation. And then restitution, just call that E if you want to. I get a bit lazy on those. So E is equal to 1/4. And that's equal to your separation speed, which is going to be W minus V, over the approach speed, which is going to be 6 cos 60. So that's your approach speed along the line of centres coming from here. And that gives you W minus V is equal to 3/4. When you work out, so you can just pop that into a calculator if you want to, or you can add them together. So we've got two simultaneous equations. So adding those, I get 3W is equal to 15 over 4. W equals 5 over 4. And V then comes out as being 1/2, but you just need to work through that. We want the speed, the velocity of A and B after the impact. So to find the velocity of A, we know V's come out as positive, so it's going that way by 1/2. Vertically, 6 sine 60 is 3√3. So the velocity of A is equal to the square root of 3√3 squared plus 1/2 squared, which I have as a decimal as being 5.22 meters per second. We're not working in vectors particularly in this question. We will do some work with vectors, but not for this one. And the angle theta, so we can take this angle with the line of centres, so that the angle theta we can take as being arctan of 3√3 over 1/2. I'm hoping I've got this written down nicely for you. I think that is 74.5. But I haven't written it down very nicely, so you can check that if you want to. And then the velocity of B is obviously 1.25 meters per second along the line of centres.